Hello, welcome to another module in this massive open online course. Alright, in today's module, let us start looking at another concept in digital communication. It's a very important concept and in fact also one of the most fundamental frameworks, which is termed as a signal space. Okay, it's slightly abstract, but it has several applications, especially in digital communications. Okay, so let us start looking at what is known as the concept of signal space. It's rather a framework. It's a framework for digital. Let's call this as an important framework for to understand digital communication. It's a framework to understand digital communication systems. Now, let us start with a simple introduction to the concept of signal space. Now, consider two pulses. Now, so far what we have been doing is we have been considering a single pulse. Now, let us consider two pulses, which we are going to denote by P1t and P2t. These are the two pulses that we want to consider, and remember, so far we have been considering only a single pulse with this property that, of course, if you look at the energy of the pulses, P square t, that is, if you look at P1 square t dt, this is equal to minus, that is energy of the second pulse. Okay, that is, if you look at energies of both the pulses, P2 square dt, that is equal to EP. Let us set them equal to 1, that is, both pulses have unit energy. Both pulses have unit energy, and more importantly, that is, both pulses are normalized to more important. And further, let us also note that this is more importantly, if you look at the inner product between the two pulses, integral minus infinity to infinity P1t P2t, this is equal to 0. That is, both the pulses are orthogonal. So, what we are saying is that there are two pulses, each pulse has unit energy, and both the pulses are orthogonal. Okay, that is the inner product. If you look at the inner product of these two pulses, the inner product is 0, for instance. Okay. Now, what we say is these two pulses, if you look at P1t and P2t, such pulses P1t, P2t, we say these are the basis functions, these constitute the basis, or let us say these constitute not just any basis, these constitute what is known as an orthonormal. These constitute what is known as an orthonormal basis for a signal space. The key word here is orthonormal. What is the meaning of orthonormal? Remember, this is formed from the two words ortho plus normal. Ortho means both these pulses are orthogonal, that is both pulses are orthogonal, and normal means that the pulses are normalized to unit energy. So, they are orthonormal pulses, which means the pulses are orthogonal and they are normal, that is they are normalized to unit energy, and these two pulses P1 to P2T form an orthonormal basis for a signal space. Now, we have to understand what is a signal space. A signal space is simply similar to a vector space, is simply a space that is formed by a linear combination, similar to a linear combination of vectors. We have a linear combination of orthonormal basis signals, that is we take alpha 1 times P1T plus alpha 2 times P2T, where alpha 1 and alpha 2 are any, these are any two real numbers. So, all such linear combinations form, so all such linear combinations are basically elements of the signal space. So, all these belong to S, which is the signal space. So, all such linear combinations are elements of the signal space. All such linear combinations of these two orthonormal basis pulses P12 and P2T, P1T and P2T, that is alpha 1 times P1T plus alpha 2 times P2T, are elements of this signal space. Okay. Now, let us take an example. For instance, let us consider a simple example. P1T equals square root of two pi cos, this is a pulse that we have already seen, and similarly now let us also take P2T equals square root 2 by T cosine 2 pi f2t for 0 less than or equal to t less than or equal to t less than or equal to t, where can we say we can say t equals integer multiples, that is k1 over f1, integer number of cycles of p1. T also contains integer number of cycles of P2, that is this condition says T, the duration, pulse duration T contains integer number of cycles of P1T, T also contains integer number of cycles of P2T. Further, number of cycles are different, that is we are assuming K1 not equal to K2, that is the number of cycles of P1T in the duration T and the number of cycles of P2T in the duration T are different. That is these two correspond to that is these two have a different number of number, correct. These two have a different integers, different numbers of cycles in the symbol duration T. Okay. Now, another way to look at this is, if you look at F1, F1 is equal to, now look at it in terms of frequency, F1 is equal to K1 over T. I can write this as K1 F0, where 1 over T equals F0, F2 equals K2 over T equals K2 over F0, where F0 equals 1 over T. So, these are different multiples. So, you can see F1 and F2 are different multiples. These are different multiples of same fundamental frequency F0. These two frequencies F1 and F2 are multiples, different multiples, K1 times F0, K2 times F0, where F0 is 1 over T. We are considering two such pulses, alright, cosine 2 pi square root of 2 over T, cosine 2 pi F1T, square root of 2 over T, cosine 2 pi F2T. Now, the reason we are considering square root of 2 over T, the scaling factor is obvious, that is we want to normalize the pulse to unit energy, that is something that we already seen, that is if you look at the energy of pulse 1, that is if you look at E1, that is equal to P1 square T integral 0 to T, or integral minus infinity to infinity actually, but it is 0 only from 0 to T. This is equal to 0 to T, well 2 over T cosine square 2 pi F1T, which is equal to 2 over T integral 0 to T cosine square 2 pi F1T is 1 plus cosine 4 pi F1T divided by 2 times dt, which is equal to 2 over T times T over 2 plus 1 over T integral cosine 2 pi F1T is 4 sin 4 pi F1T divided by 4 pi F1 between the limit 0 to T. This is equal to 1 plus, of course, this quantity we have seen before also, this quantity is 0. So, this is equal to 1, which is equal to EP. Similarly, if you look at energy of pulse 2, naturally that is also similarly E2 equals minus infinity to infinity P2 square dt, that is equal to 1, that is equal to EP. Now, let us consider the inner product. Consider now the inner product. Consider now the inner product. If you look at the inner product, what is going to happen is we have integral minus infinity to infinity P1 T P2 T dt, that is equal to integral minus infinity to infinity, substituting P1 and P2 square root of there is 2 over t times cosine 2 pi f1 t cosine 2 pi f2 t dt, which is equal to integral minus infinity to infinity 1 over t. Now, we are going to use the result 2 times cosine a cosine b is cosine a minus b minus cosine a plus b or plus cosine a plus b. So, this is going to be cosine 2 pi f1 plus f2 t plus cosine 2 pi minus f2 f1 minus f2 t t dt. Now, look at this. If you look at this, f1 plus f2 equals k1 over t plus k2 over t, which we can say this is k1 plus k2 times f naught, and f1 minus f2 is similarly k1 minus k2 times f naught. And therefore, the integral is basically, if you look at this integral cosine 2 pi f1 plus f2 times t, this is sine 2 pi f1 plus f2 times t. So, this is equal to, I can write this as 1 over t sine 2 pi f1 plus f2 times t divided by 2 pi times f1 plus f2 evaluated between the limits 0 to t plus 1 over t sine 2 pi f1 minus f2 times t divided by 2 pi times f1 minus f2 0 to t. We already seen f1 plus f2 is k times f naught. So, that is basically 1 over t sine 2 pi k1 plus k2 f naught divided by 2 pi k1 plus 2 pi f1 minus f2 f1 plus f2 is 2 pi k1 plus k2 f naught between the limit 0 to t plus 1 over t sine 2 pi k1 minus k2 into t into f naught t 2 pi k1 minus k2 into f naught 0 to t. Now, you can see, of course, sine of 0 is 0, sine of 2 pi k1 plus k2 f naught times t is 1, this is equal to, well, this f naught times t, f naught equals 1 more t. So, this is equal to 1. So, this is sine 2 pi k1 plus k2 sine of 2 pi integer multiple of 2 pi, this is equal to 0. Similarly, sine of 2 pi k1 minus k2 f naught t equals sine of 2 pi k1 minus k2, this is equal to 0. So, therefore, if you look at both these terms, these are 0, that is, if you look at both these terms are 0, and therefore, this integral we have the inner product p1 t p2 t dt, this is equal to 0. So, we have inner product is equal to 0. Okay. So, we have inner product equal to 0 implies P1T P1T P2T are orthogonal. So, we have unit norm. Okay. So, we have two pulses P1T P2T which are unit norm, also they are normalized to have unit energy, both have unit energy and they are orthogonal. Okay. So, these two properties are satisfied. Let us again write that clearly. We have P1T these are orthogonal and they have unit energy as well, implies they form an orthonormal basis. So, these two form an orthonormal basis for the signal space. And what is the signal space? The signal space is formed by all linear combinations alpha 1 P1 T plus alpha 2 P2 T, that is alpha 1 square root of 2 over T cosine 2 pi F1 T plus alpha 2 square root 2 over T cosine 2 pi F2 T. So, this is basically your signal space. So, they form an orthonormal basis, they form an orthonormal basis for the signal space. Okay. And therefore, now we are going to employ this signal space to divide to design modulation schemes, various modulation schemes, describe the performance of those modulation, describe the various describe how to construct the modulation scheme, describe how to construct the demodulation scheme corresponding to each modulation scheme, and also see what is the performance, that is the bit rate performance to of each such digital modulation scheme. Alright, each such new digital modulation scheme which is constructed using the employing or based on this concept or based on this framework of signal space. And we are going to look at several interesting digital modulation schemes which rely in this on this abstract concept of what is known as a signal space, which is generated by multiple orthonormal, that is orthogonal and normal basis signals or basis pulses, what we have seen in this case. Okay. So, let us stop here. Thank you very much.